The phenomenon known as emergence is a complex concept yet still knowable if taken in pieces. Let's look at the math. Section 1. The unseen choreography of the everyday. A single bird cannot make a flock. A single car cannot create a traffic jam. A single neuron is not a thought. Yet, in each case, when you bring many of these simple parts together, something new and often surprising appears. The individual parts follow very local, very simple rules, but the group as a whole exhibits a complex, coordinated behavior that seems to have a life of its own. This spontaneous creation of order and complexity from simple components is what scientists call emergence. It is one of the most profound and puzzling concepts in all of science, forcing us to ask a very deep question. Is this higher-level order truly real, or is it just a pattern we see when a system becomes too complicated for us to track every part? Consider a murmuration of starlings painting the dusk sky, with its fluid, shifting shapes. Each bird is only paying attention to its immediate neighbors. It follows a simple, instinctual script. Stay close but not too close. Match your neighbor's speed, and steer toward the average position of the group. No single starling has a blueprint for the magnificent, swirling pattern the flock will create. There is no leader, no choreographer conducting the show. The pattern emerges from the collective, a beautiful and ghostly whole that seems to have its own logic and grace. This raises a fascinating contest of ideas. One view, called weak emergence, says this is just computation. The other view, strong emergence, suggests something genuinely new has come into being. Section 2. Tool 1. The grid of life. The first mathematical tool we can use to explore emergence is called a cellular automaton. Imagine a vast grid of squares, like a checkerboard that stretches on forever. Each square or cell can be in a simple state, such as on, or off, black, or white. Time moves forward in discrete steps. At each step, every cell looks at the state of its immediate neighbors and then updates its own state based on a very simple, unchanging rule. This tiny local rule is the only law in this universe. There is no master plan, no global coordinator telling the cells what to do. The entire system evolves based on the parallel actions of these simple, identical components. The most famous example is John Conway's Game of Life. The rules are incredibly simple. A living black cell with fewer than 2 living neighbors dies from loneliness. A living cell with more than 3 living neighbors dies from overcrowding. A living cell with 2 or 3 living neighbors survives to the next generation. Finally, a dead white cell with exactly 3 living neighbors becomes a living cell. That's it. From these 4 simple rules, an astonishingly rich and unpredictable world emerges. You see stable patterns that stay fixed forever. You see oscillating patterns that blink back and forth like traffic lights. Most surprisingly, you see patterns that move across the grid, which Conway called gliders. These little arrangements of 5 cells behave like tiny creatures, maintaining their shape as they travel diagonally. Other more complex structures have been discovered, called glider guns, which are stationary patterns that periodically spit out new gliders. Section 3, Tool 2, the edge of chaos. Our second tool comes from the study of nonlinear dynamics and a concept popularly known as chaos theory. In a simple linear system, the output is directly proportional to the input. If you double the cause, you double the effect. This makes the world predictable and easy to understand, but most of the real world is not linear. In nonlinear systems, tiny changes in the input can lead to enormous, disproportionate, often surprising changes in the output. This sensitive dependence on initial conditions is famously known as the butterfly effect, where the flap of a butterfly's wings in Brazil could, in principle, set off a tornado in Texas. This unpredictability is a powerful form of emergence. A classic mathematical example that shows this behavior is the logistic map. It's a very simple equation used to model population growth in an environment with limited resources. The equation has a single parameter which you can think of as the fertility rate. When this rate is low, the population settles down to a stable, predictable number. As you slowly increase the fertility rate, something interesting happens. The population no longer settles to a single value, but starts oscillating between 2 values. Increase it a little more, and it oscillates between 4 values, then 8, then 16. This period doubling continues until, at a certain critical value, the system's behavior becomes completely chaotic. In the chaotic regime, the population never settles down or repeats. It fluctuates in a way that looks completely random, even though the equation generating it is perfectly deterministic and simple. Two starting populations that are almost infinitesimally different will, after a short time, have completely divergent futures. You can no longer predict the long-term behavior. The system has emerged into a state of chaos. This mathematical tool teaches us that even the simplest deterministic systems can generate behavior that is intrinsically unpredictable. The chaos is an emergent property of the nonlinear equation. Section 4, Tool 3, the rules of the flock. Our third tool is the agent-based model, or ABM. This approach is similar to cellular automata, but instead of stationary cells on a grid, we have mobile agents moving around in a virtual space. Each agent is a discrete, autonomous entity. It has its own internal state and a set of simple behavioral rules. These rules dictate how the agent perceives its environment, and how it acts based on those perceptions. Crucially, agents typically only interact with their local neighbors. There is no central controller or global information guiding the system. Complex system-wide behavior emerges from the bottom up, from the multitude of local interactions between the agents. A beautiful and influential example is the Boyd's model by Craig Reynolds, 1986. Each Boyd follows just 3 simple rules. First, separation. Steer to avoid crowding local flockmates. Second, alignment. Steer toward the average heading of local flockmates. Third, cohesion. Steer to move toward the average position of local flockmates. That's it. Release many Boyds programmed with these rules and they organize into a fluid flock. The flock can navigate around obstacles. The flock can split to avoid a predator. The flock can seamlessly merge back together. None of this group behavior is programmed into any single Boyd. The intelligent, adaptive behavior of the flock is an emergent property of the system. Section 5, Tool 4, the tipping point of connection. The final mathematical tool we'll consider is network science. It studies the structure and dynamics of systems made of interconnected nodes. The nodes can be anything: people in a social circle, computers on the internet, neurons in the brain, proteins in a cell. The links represent relationships or interactions between them. Network wiring profoundly affects behavior. Many dramatic emergent phenomena happen at a network's critical tipping point, called a phase transition. Imagine many isolated nodes. Start adding links at random. At first, many small, disconnected clusters form. The network is fragmented. Keep adding links, something magical happens. At a specific connectivity threshold, a giant component suddenly emerges. A single massive cluster spans much of the network. Below the threshold, spread is local and limited. Above it, it can reach almost everywhere. The system has undergone a phase transition, like water freezing into ice. Mathematics shows emergence can be abrupt, not always gradual. A single parameter can flip the system past its critical value. The giant component appears all at once. Connectivity is key. The mathematical tools we've explored, cellular automata, nonlinear dynamics, agent-based models, network phase transitions, all provide compelling evidence that complex, higher-level patterns can spontaneously arise from simple local rules. They show that emergence is not magic, it's a natural consequence of certain kinds of systems, but this leads us to a deep and contentious philosophical debate. When we see a glider in the game of life or a flock in a Boyd simulation, are we looking at something genuinely new and real? This debate is often framed as a contest between two main viewpoints: weak emergence, strong emergence. Both sides agree that novel and unpredictable behaviors can appear in complex systems. They disagree on the fundamental nature and causal status of these behaviors. It's the difference between seeing the world as a one-way street, where all causality flows from the bottom up, and seeing it as a two-way street, where higher levels of organization can reach down and constrain the lower levels from which they are built. The concept of weak emergence is the more conservative and widely accepted view within the scientific community. It argues that emergent properties are real in the sense that they are observable patterns, but they are not fundamentally new. They are, in principle, completely explainable and derivable from the low-level components and their interactions. The emergence is an epistemological phenomenon. It has to do with our knowledge. The higher-level behavior is surprising and hard to predict for us, because the sheer number of interactions is too vast for our minds, or even our fastest computers to track in detail. But there are no new laws of nature coming into play. In contrast, the concept of strong emergence makes a much bolder claim. It proposes that at certain levels of complexity, genuinely, new properties and causal powers can appear that are irreducible to the underlying physics. These new, higher-level properties can exert a real influence on the components that make them up, a phenomenon called downward causation. According to this view, the emergent whole is not just a pattern we observe, it is an active player in the world with its own causal efficacy. The laws governing the whole are not derivable from the laws of the parts. This is a claim about ontology, about what is fundamentally real in the universe. The case for weak emergence is straightforward, pragmatic, and grounded in the successes of computational science. Proponents of this view argue that the emergent phenomena we see, both in nature and in our models, are ultimately the result of computation. If you have a powerful enough computer and you know the precise starting state of all the parts and the exact rules they follow, you can simulate the system's evolution forward in time. The simulation will, step by step, reproduce the higher-level behavior perfectly. The flock will form, the glider will move, the chaos will unfold. There is nothing in the final state of the flock that was not, in principle, contained within the initial state and the rules. From this perspective, emergence is a label we use for behavior that is computationally irreducible. This means there is no shortcut. You cannot write down a simple equation that tells you where the flock will be in 1,000 steps. The only way to find out is to run the simulation for 1,000 steps. The behavior is unpredictable in practice, but not in principle. The higher-level patterns, like the shape of the flock, have no causal power of their own. The flock's shape doesn't cause the birds to move. The birds' movements, following their simple rules, cause the flock's shape. All the causal work is being done at the lowest level. There are no new life forces or mental substances. There's just one set of fundamental laws playing out at ever-increasing scales of complexity. The power of this view is its simplicity and its alignment with the scientific method. It doesn't require us to invent new kinds of causation or new levels of reality. The argument for strong emergence is more subtle, more speculative, but also more tantalizing. Proponents of strong emergence point to the concept of downward causation. They argue that once a higher-level system becomes established, a living cell, an organism, a human society, it can create a new context that constrains and directs the behavior of its own components. The whole, in a very real sense, begins to govern its parts. Consider a single protein molecule inside a living cell. Its behavior is, of course, governed by the laws of quantum chemistry. But its function, what it actually does, is determined by the needs of the cell as a whole. The cell's structure and organization act as a set of boundary conditions that select which of the protein's possible behaviors are realized. The protein is a slave to the cell's purpose. The conscious intention to raise your arm seems to be a mental, high-level cause that results in a cascade of low-level physical events. Neurons fire, signals travel down nerves, muscles contract. Similarly, abstract social constructs have immense causal power: laws, money, corporations. The value of a dollar bill is not a property of its physical ink and paper, it is an emergent property of a collective belief system. Yet this abstract belief causes people to build bridges, fight wars, dedicate their lives to acquiring it. The higher-level social reality appears to be pushing around the lower-level physical world. The higher-level laws and structures are the most stable, efficient, and meaningful descriptions of the system. They represent genuine patterns and regularities in the world. So, where does this leave us? Is emergence a mere story we tell ourselves, or is it a fundamental force of creation? The most reasonable conclusion is that both weak and strong emergence offer valuable perspectives. Complexity science proves weak emergence is real and pervasive. Simple local rules and computer models mirror fundamental physics. Those models show complexity, unpredictability, and structure arising bottom-up, without a designer. Strong emergence is harder to prove, but it highlights higher levels of organization: a cell, a brain, a society. Once such a structure has emerged, it becomes a new environment that creates its own rules. Those rules have real predictive and explanatory power and shape future events. Whether you call it downward causation or a change in context, the whole begins to shape the parts. The world is built in layers, each with its own science and causal regularities. Emergence is an ongoing, reciprocal process that builds reality layer by layer. Back to the flock, more than birds, a dance of simple rules and collective coherence. A system both deterministic and creative, reducible in principle, yet surprising in practice. Perhaps, emergence isn't just a scientific curiosity, but the universe's primary creative engine. the hidden engine lifting the universe from the Big Bang's uniformity to our rich, mindful cosmos today. Math isn't magic, it's everywhere.